Hello and welcome everyone. It's a landmark moment, and I'm thrilled to say you are part of it. This is the first ever South Africa Wolfram User Conference, and we are making history together. Whether you are joining us from a university lab, a corporate office, or from your favorite coffee shop, thank you for being here. Today is all about ideas, innovation, and inspiration powered by Wolfram Technologies. My name is Farid Pasha, and I'll be your host for this exciting journey today. We have curated a lineup of five brilliant speakers who will take us through everything from engineering uncertainty to predictive financial modeling, all using Wolfram language. Let's dive into our first session. Our first speaker today is Dr. Mark Rollins, who is the Executive Chairperson and Chief Engineer at Energy and Combustion Services Group.
Hi from South Africa. I'm Mark Rawlins, the Chief Engineer at Energy and Combustion Services. Today I'd like to talk to you about the application of uncertainty as implemented in Wolfram via a small selection of the powerful functions that are available in 14.3. Practical application of uncertainty in engineering computations can be complex and time-consuming. And if you don't have the right analytical tools, it is a frustrating endeavor. Without convenient access to these tools, many engineering computations lack associated uncertainty estimations. So to the rescue is Wolfram, that is a rich and powerful framework for uncertainty estimation. I'm going to demonstrate a small selection of these uncertainty functionalities in both practical application and how to use the functions themselves. Here is a simple description of error propagation as generated by Wolfram Notebook Assistant, showing how error propagation operates and the Wolfram implementation. It is a basic description, however, I'm going to go through some of these details in a moment. I'm going to focus on the following: a demonstration of the function around, which represents an approximate number with uncertainty. And for symbolic generation of these uncertainty functions, I'm going to talk about around using variables with uncertainty and combine them with specific compute functions. I'll also show how around operates with parameterized distributions. Then mean around, a high utility function for our kind of work when you're doing experiments and trials and expanded uncertainty values. Then around replace, where one can propagate uncertainty at different series expansions of order n. Further, I'm going to show you the Monte Carlo simulation of error propagation that has a similar purpose to around replace and handles deviations from error propagation assumptions. Also included is an industrial application of the tools. Finally, a brief exposure to uncertainty in regression modeling with Wolfram. For the demonstrations, I created three example compute functions. One is a simple additive function. There's a product function. And the third is a nonlinear function to compute using the variables x1, x2, and x3. We're going to compute those. If you then said there was uncertainty in x1, defined by round using the mean of x1 and the standard deviation x1, and the same for x2 and x3, you create three uncertain objects as such, mean plus or minus the standard deviation. Once you define these uncertain objects and insert them into the additive function, you get a symbolic representation of the addition of the means and quadrature combination of these uncertainties, for example, as such. If applied to the product function, you then get the certainties properly propagated symbolically, shown here. You could also apply the nonlinear function as before, and you get the symbolic uncertainties for that. And if you apply it to any other function, for example, it seems unlimited in terms of the way you can propagate these uncertainties. For example, if you applied the uncertainties of x1 and x2 in a log function, you would get this uncertainty representation. You can also use parameterized distributions within a round. So for example, let's say we fit a normal distribution for x1 where you have a mean centered around 10 and a standard deviation of 5, and you define the distribution as such. You get this normal distribution. We can also define a triangular distribution with parameters min and max. Because I want to define the standard deviation in terms of min and max, we can go and find out what the min and max value should be to represent the standard deviation like this. The third is normal distribution again, but centered around a different mean. Now, if we had to use these distributions within the above predefined compute functions, you would get the correctly propagated results of y1, y2, and y3 as follows. So for these examples, we have 80 plus or minus 7 for the additive propagation. There's also 10,000 plus or minus 6,000 for the product propagation, and there's 1,200 plus or minus 943 for the nonlinear propagation. You can also pull out the details of these uncertainties like this, the value of uncertainty and the interval, shown here for the uncertainty in Y1. You can also get means of lists with uncertainty. For example, the function mean around. The mean around function is specific in that it works on the standard deviation divided by the square root of n of the list, where the standard deviation divided by the square root of n is known as the standard error of the mean. This is handy when you use expanded intervals on uncertainty by multiplying by the standard error, or multiplying standard error by the studentized t-value. For example, if I generate a list of some random data through the normal distribution, as shown here, then compute the mean around for that, the result is the mean and the standard error of that mean. So this 0.18 is the standard error. You can also compute, let's extract the interval for that. This could be applied, for example, with a confidence level-based uncertainty and using a function repository resource like the student t-value to compute the t-value at the same time as the mean around is being computed, for example, like that. We could also look at this in a bar chart, for example, shown here, where you've shown the standard error on top of the mean, as well as the expanded standard error side by side. Noting that many Wolfram charting and plotting functions simply deal with uncertain objects of the data. I mentioned that with a round, the error propagation is done as a first order expansion. This is not a limitation in Wolfram. You can also use series expansion to any order, to be demonstrated here by using a highly nonlinear function like this and the Wolfram function around replace. Now, an example where the uncertainty is relatively small compared to its value, and checking the difference between the first order and second order propagation, you get the following results. For the first order, the result is a value of 32 plus or minus 0.8. For the second order, the results are typically the same as expected, 32 plus or minus 0.8. For now checking the results when the uncertainty is relatively small compared to the Now checking the results when the uncertainty is relatively large compared to the value as shown here. Just compute these quickly. For the first order, the result is an expected high uncertainty with a value 32 plus or minus 0.16. For the second order propagation, you get a different value and uncertainty. Therefore, one needs to pay attention to the size of the uncertainty relative to its value and the compute function you're using when you're doing the error propagation. But in Wolfram, you can easily experiment with the results of different setups and assumptions. Now moving on to Monte Carlo methods. There are situations where the propagation of uncertainty can be highly complex. Say one is uncertain about assumptions on the data generating process, especially with nonlinear models, non-Gaussian or asymmetric uncertainties, correlated measurements, and complex measurement problems. Then you'd want to employ Monte Carlo propagation of errors. This is well defined in the JCGM. By example, I showed earlier the normal distribution, the triangular distribution, and the normal distribution again. These are processed through predefined compute functions as originally set up to give you the result. There are well-defined algorithms for doing Monte Carlo simulations and error propagation within these guidelines, and it's worthwhile having a look at these. We can now set up the Monte Carlo trials using the above algorithm. Typically there's 100,000 trials, but you could also have anywhere between 100,000 and 1 million trials, and these can be optimized depending on the problem at hand. Just input that quickly. We can now take random samples using random variate from these distributions and the number of trials, where the lists are of length m, representing the sampled x1, x2, and x3 from these distributions. So just compute those quickly, those samples. You can now apply those samples through the additive function, the product function, and the nonlinear function. By example, like this. I'm not displaying these lists because they're very long. Now that I've done the previous compute, let's see, for example, what the distribution looked like for the additive function result in Wolfram. This can be found using fine distribution, as shown here. You can also find the value, the uncertainty, and interval for each result, y1, y2, and y3, shown here for y1. Now using the additive function and comparing the Monte Carlo propagation to around, just compute that quickly. You'll notice that the uncertainty in the results from both methods are reasonably close, as expected. You can see over here like this. So the intervals are reasonably close, and the means and standard deviations. You could also look at the Monte Carlo results as follows through the histogram and the propagated uncertainty through the additive function. Now using the nonlinear function as defined earlier, you can also get the distribution of the Monte Carlo results of fine distribution. Just compute that quickly. And also you can compute around for the parameterized distributions processed through the nonlinear function that looks like this. You'll notice that the means and the uncertainty intervals are somewhat different, indicating a need to propagate error using around at a higher order expansion. As you can see here, the intervals and the means and the standard deviations are somewhat different. So you could use around replace with a second order expansion like this. The result is a mean and error interval which is much closer to the Monte Carlo values. So over here, this is the Monte Carlo values. This is the around replace. The intervals are similar. So you could always use around replace as a comparison to the Monte Carlo. You could also look at that distribution of the Monte Carlo like this. There are also many ways to solve the error propagation problem, with examples demonstrated here for around replace, and Monte Carlo. Depending on how you wish to deal with assumptions, simplifications, the Wolfram language allows lots of flexibility in this regard. Now moving on to an industrial application of an air compressor used in a pet beverage bottle blowing service. Here there's a reciprocating air compressor. It is providing compressed air to a blow molding machine using bottle preforms, which are heated and then blown into the mold to take the shape of the bottle. The engineering problem was that the plant needed its energy efficiency and throughput capacity increased. For the new plant specification, the energy consumption needed to be confirmed via historical measurement for the different production levels. However, the energy and power history was not recorded, but the operational conditions were. The engineer resolved this by computing the polytropic compression work and then integrating this work done per unit mass and then converted that into power and energy, noting that there is a requirement to estimate the uncertainty of these values. When we look at the polytropic compression curve as specific volume versus pressure, the polytropic line is between the adiabatic and the isothermal lines, with the pressure times volume to the power of n is constant, where n is the polytropic index. So this is the function we're going to use to estimate the work. I can get the formulas for a polytropic process using Wolfram formula data like this. I'm interested in the work and pressure and temperature relationships. So here's the work here, and here's the pressure and temperature relationships. In these forms, the relationships are related to volume. However, it is not convenient to use specific volume because this value is not directly measured with the instruments. However, if I can get the ideal gas law like this, which is PV equals nRT, I can relate the pressures and temperatures to R. Then I can define the work in relation to temperature, polytropic index, and R. And since this relationship here holds, then you can compute the polytropic index as such. Now that the equations have been defined, what I've done here is build a polytropic work function. It takes the measured air operating parameters, inlet pressure, inlet temperature, outlet temperature, the gas constant, and the measurement uncertainties in these values. This is defined in a small module where the units are converted as well as scaled to the uncertainties. Here the polytropic index and the work per unit mass is computed and placed in a variable called results. So let's get going with this. If we want to use this function, we define the work parameters. Here the compressor parameters are P1 at atmospheric pressure, 101 kPa, P2 at 751 kPa, the inlet temperature is 26 degrees, and the outlet temperature is 81 degrees. You can then compute the gas constant using Wolfram physical constant and thermodynamic data like this. You can also specify the uncertainty that's going to be used in scale. For example, the uncertainty is 1% for the pressure and 0.05% for the temperature. Using the above, for one instance observation of pressures and temperatures, you can compute the polytropic index and the specific work with the uncertainties. So using the equation or the function defined above, you end up with a polytropic index of 1.092 with its uncertainty and a work required per kilogram of air of 172 kilojoules per kilogram of air with its uncertainty of 0.24. You can also look at the input form of those results like this, getting the around and the quantities of the answer in joules per kilograms. There's a mass flow meter on the compressed air line measuring the mass at a 1% relative uncertainty. There's one recorded instance showing a mass flow of 2,000 kilograms of air per hour. And there's a mass flow uncertainty. The mass flow and its uncertainty can be computed as follows. There's also a motor and compressor efficiency of 70%, as well as the uncertainty in that efficiency. Just compute those. So let me quickly compute the values and create a table specifying the quantities, the mass flow, the output values, and so on. With that, you'll have a table of values for this one observation. So let me just go and compute those quickly like that. So under these conditions of uncertain inlet pressure at the correct units, the outlet pressure, the inlet temperature, the outlet temperature, the specific gas constant, the mass flow, and the compressor efficiency, you can compute a polytropic index as shown here with its uncertainty, the polytropic work, again in its correct units, the polytropic power, and the motor power shown here as watts. You end up with a motor power of 136 kilowatts with an uncertainty of 23 kilowatts, which was the whole objective, to get what the motor power would be for a specific flow rate of air with its uncertainty. How is this applied? So we take the polytropic compute function that we had above that generated these demonstration values. We place that in a compute pipeline with the data acquisition system from the SCADA, where you apply transformation functions and then compute these uncertainties as you move along the timeline. Now, if you generate this motor power over time, if you integrate this motor power over time, you'll get the energy values in kilowatt hours. Now, briefly touching on some other detail, you could easily get the symbolic uncertainty of the polytropic work. If you set up the uncertainties of the measured parameters, say pressure and temperatures, specify the equations for computation, and if you ran these, you'll get a full expression of how the uncertainty was computed using the first order expansion. So for example here, these are the uncertainty computations for the work and the polytropic index. Also in this project, the data is set up in a SQL database. There's a lot of data, millions of rows. And in Wolfram, you can set up the database referencing with all your credentials. You can connect to the database and go and fetch the data and inject that straight into a tabular object, showing you, for example. This makes it very convenient to exploit all the power of tabular. And even though tabular has powerful transformation methods, you can do all kinds of SQL transformations on the fly, for example, an end join shown here. Wolfram also has an impressive range of uncertainty capabilities with regression modeling. One shown here is a linear model fit. By example, you can create a data set and fit the defined model. Let me just do that quickly. Linear model fit also has many properties for diagnostics and prediction capabilities. So pull out some of the properties here. You can compare the response to the predicted response. For example, if I made a plot like this, you can also get the mean prediction confidence intervals. So from the model, you can get the observed value, the predicted value, the standard error, and the confidence interval of that prediction. Very handy indeed. You can also obtain results for single prediction confidence intervals, shown here. Again, observe the predicted, the standard error, and the confidence interval. You can also, for all your data, get pull all into a list the confidence intervals. You can also get the equations that were used to produce the mean prediction bands at a confidence interval of 0.99, for example. These are the equations here. And you could also use the model, when using the model, you can compute the mean prediction for a specified input value, for example, over here like this. So for 4 and 1, this is the prediction interval. Also, you can get the uncertainties in the parameter estimates. So you have your best fit parameters, your standard errors on that, your t-statistics, your p-value, and your confidence interval of those. So that's a short introduction on Wolfram uncertainty, compute and capabilities and functions. I trust you have gained insights and will apply uncertainty in your work using these powerful tools.
Thank you, Dr. Rollins, for that insightful presentation. I think let's move on with our next presenter, who is Ankit Naik. He's the application engineer and Wolfram certified instructor at Wolfram Math Core. He will be telling us how and exploring us how the Wolfram tools are used to model and optimize energy systems from local installations to national grids. Welcome, Ankit.
Hello, everyone, and welcome to this talk titled From Solar Rooftops to Power Grids. I'm Ankit, an applications engineer from the Wolfram System Modeler team. In this session, I'll walk you through a use case that highlights why simulation is essential in driving the energy transition, from understanding household behavior to designing resilient power systems. The world is electrifying and the pace is accelerating rapidly. In the next 6 years, global electricity demand is expected to rise by around 6,500 terawatt hours, according to the International Energy Agency. To put that into perspective, that's like adding another United States worth of electricity demand. And the US is already the second largest consumer of electricity after China. This surge is driven by data centers, the electrification of heavy industries, electric transport, and other emerging sectors. But while global demand keeps growing, let's take a moment to look closer to home and see what the current reality looks like. For this presentation, let's focus on South Africa, a country that reflects the situation in many developing economies around the world. It has a growing economy and a young population, especially when compared to developed nations. However, since 2018, South Africa has experienced frequent load shedding, largely due to aging power infrastructure and insufficient generation capacity. While the situation has improved somewhat in 2025, load shedding remains a daily reality for many households. What's more concerning is that costs are rising too. Compared to 2003, the residential electricity tariff has increased sixfold. So, while people are paying more for electricity, they're actually getting less reliability. In short, bills are going up while the lights are still going out. Unreliability isn't just a theoretical concept, it has real, everyday consequences. Your fridge warms up and the food inside spoils. Your lights go out in the middle of an important task, maybe even a job interview. Or your washing machine stops halfway, wasting both time and energy. So, how do we move towards a more reliable power supply, one that's built on informed technical decisions without spending a fortune on oversized systems? Let's explore our use case through a household in Johannesburg. Before we look for solutions to improve reliability, it's important to first understand the electricity demand and identify the main contributors. Climate plays a big role here, influencing seasonal heating and cooling needs. So, let's start by gathering data for Johannesburg. Using the Wolfram language, we can easily connect to open data sources like PVGIS to extract solar radiation and temperature information for the region. Once we have this data, we can build a generic household energy model based on engineering first principles to estimate electricity demand from different sources. Now, before diving into the details of that model, let's look at what the simulation results tells us. For a 100 square meter house, the model predicts an average consumption of around 650 kilowatt hours per month, which stays fairly consistent throughout the year. The major contributors to this demand are electrical appliances, followed by water heating and space cooling. During the winter months in South Africa, roughly May to August, the demand shifts towards space heating, while the rest of the year is dominated by cooling loads. As you can see from NREL data, the electrical load, which includes lighting, cooking, refrigeration, and television use, makes up the largest proportion of household energy demand for a middle income group. This is followed by water heating and then by space heating and cooling. Now let's look at one of the submodels I use to predict space heating and cooling demand. This is a house model built in Wolfram System Modeler. Here, the thermal inertia of the building is represented using a heat capacitor component. Here, multiple heat sources and sinks are connected to it through input signals such as solar radiation, ambient temperature, and heat losses to the surroundings. We also have a controller in the model that maintains the indoor temperature. It automatically switches on the radiator when it's cold or activates the air conditioner when it's hot. In addition, there is a component that accounts for heat generated by occupants inside the house. The plot you see here shows the simulated results across 10 different years, capturing how the building responds to changing seasonal conditions. I won't go into all the other submodels now, but if you're interested, you can find more details in the link provided here. To summarize, what we have seen so far is a simulated model of a household in Johannesburg, capable of predicting energy demand based on different heat loads and climate factors. Next, let's look a bit deeper into the resulting demand profile over a span of a few days to understand how load fluctuations occur in practice. If we dig a bit deeper into our household model, we can start to observe some sharp transitions in the energy demand as shown in this plot. A lot of data contributes to these variations: heating or cooling based on temperature, lighting that switches on and off depending on solar radiation levels, and other appliance usage patterns. Still, we can identify some general trends. After midnight, the demand is mostly from heating and cooling loads. During the day and early afternoon, when there is sunlight, fewer people at home, the demand drops to a low level. Then, in the evening, we see a few distinct peaks caused by activities such as cooking, using the dishwasher, or watching television. This profile represents a typical residential load. Now, if we shift perspective and look how an energy provider views the same situation, aggregating data from homes, offices, industries, and other facilities, we see a different pattern. Such a plot usually shows two main peaks: one in the afternoon when the offices are running at full capacity, and another at night when households become active again. My current model focuses only on residential consumption, so it does not include the daytime commercial peak, but the overall trend remains similar across most regions. So far we have looked at the demand side through simulation. Now let's turn to the grid side and understand what happens when demand and supply fall out of balance. When we talk about the grid, you often hear terms like frequency and voltage. Let's use a simple model to understand why load shedding occurs. One of the main reasons is that demand exceeds supply, and as a result, the grid can no longer maintain a constant frequency. Imagine a gas turbine generator with a rotating shaft. The rotational speed of this shaft determines the frequency of the AC power it produces. In normal operation, the turbine rotates at constant speed, generating electricity at around 50 Hz. As the demand increases, the controller tries to supply more power by increasing torque. Initially, the rotational speed stays stable and the frequency remains close to 50 Hz, with only minor fluctuations as the controller adjusts. But as the load continues to rise, the turbine eventually reaches its maximum deliverable power. Beyond that point, it can't increase torque further, so it starts losing rotational speed. This causes the grid frequency to drop below 50 Hz. A falling frequency can quickly affect all connected equipment, from household appliances to industrial machineries. And to prevent that, the grid operator must shed some of the load, which is what we experience as load shedding. Now that we've understood how demand dynamics and grid stability interact, let's look at what we can do at home to manage our own power usage and even help make the grid more resilient. Let's start by adding a battery to our household model. In the same diagram that I used earlier for the grid, I have now extended it by including an electrical battery system. All the components you see in this system model diagram are built using free open libraries that are supported by Wolfram System Modeler. Once the setup is ready, I can easily experiment with different battery types and capacities, and then simulate how the system performs. In this example, I began with a 10 kilowatt hour battery, which roughly matches the daily requirement of this household. And to make the concept clearer, I simulated a simplified scenario where the grid supply is limited to 800 watts, while the household peaks at around 1 kilowatt during the evening hours, roughly between 5 to 9 pm. In a traditional setup, this shortfall would cause a power outage or load shedding. But in this model, the battery compensates by supplying the total energy during that time window. So from this simulation, I can also calculate how much stored energy is needed to cover an entire blackout period. In this case, about 10 kilowatt hours. This kind of model can be used to explore strategies like peak saving, where you use stored energy during expensive tariff hours to reduce electricity costs. The advantage of simulation is that it lets you design and test different storage configurations before making any real investment. Now, let's move to the next step by adding rooftop solar to our system. Now, let's add a rooftop solar to our model and make the household operate independently of the grid. In this version, I have replaced the grid connection with a solar power model, which can be parameterized using real design data from commercially available solar modules. Once the setup is complete, I can simulate the system to see how it performs and whether the sizing of the solar array and battery is appropriate for my household's needs. In this plot, the blue curve shows the solar power generation throughout the day. You can see that during the afternoon, when the sunlight is abundant, the solar energy is used to meet household demand and to charge the battery. The subplot below shows the state of charge of the battery. It increases towards 1 during the day as the battery charges and then gradually discharges in the evening, reaching a minimum of around zero point 0.5 by night. With a model like this, I can now answer practical questions such as what type of solar panels are best suited for my home? What battery capacity should I choose to ensure reliability? By simulating the scenarios first, I can make data driven design decisions before spending money on hardware. This type of model is not limited to a single residential building. It can easily be scaled up to represent entire communities by adding multiple demand centers. In such a setup, the households can share energy resources, distribute their storage costs, and have solar panels spread across the community, making the system more cost effective and resilient. In the simulation shown here, you can see that after around 9 pm, the battery is no longer able to deliver the required power. The state of charge drops to zero, indicating that the battery capacity is insufficient. So, in this case, we would need to choose a larger battery. This demonstrates the true advantage of simulation. You can make a model, you can reparameterize it easily, add new components, scale up the system, and study different load patterns or configurations. You can also include realistic data such as temperature, solar radiation, and household demand to test a wide range of operating conditions. Beyond that, you can even simulate fault scenarios, for example, during maintenance periods or unexpected outages to answer practical questions like how much backup power is needed to meet the demand, what happens if one subsystem goes offline. And by doing this virtually, we make well informed, low risk decisions about how to design and manage reliable energy systems, from individual homes to entire neighborhoods. To summarize what we have explored in this presentation, we saw how load shedding disrupts daily life and how simulation helps us understand and solve this challenge step by step. We used models to study household energy demand, simulate batteries to find the right size, and integrate PV systems to achieve greater reliability even during blackouts. We then extended the same approach to community scale systems, showing how one model can be reused and scaled to design grid independent neighborhoods. In short, we saw how simulation makes scenario testing easy, helping us make smart, data driven energy decisions before making real investments. In this presentation, we moved from grid dependence to grid independence and ultimately to the idea of grid support, where households not only consume power but also contributes to grid stability. Simulation empowers us to make smarter design decisions and helps us make the right energy choices for our homes and communities. Thank you.
Thank you, Ankit, for that powerful look into the energy modeling in simulation environment of System Modeler and how it integrates with the Wolfram language for computation, visualization, and control design.
For people who are new to System Modeler is a modeling and simulation tool by Wolfram. It has a lot of pre-made built-in libraries, which has different engineering components from different fields, electrical, mechanical, and so on, which you can just drag and drop to create models of different physical as well as social systems. So, for example, this is one of the model that we showed that we saw uh, in the presentation, where you have a model of a PV plant, which consists of where you can specify the PV module characteristics, and then you can find out, and then you can produce current from it, which then you can combine with the household demand and other things. So the thing is, we have a lot of examples from different fields, and this is our system modeler like web page, of course. Here, depending on your domain, if you are from the energy domain, aerospace, or even life sciences, you can find different pre-made examples where you can just let me just see if you go into one of those models, you find out, okay, what are the different models that are used, uh, what was the use case of those models, and some of those models will also have downloadable uh, examples. Let me see if I have one. So for example, this is one of the example where we model the motion of the satellite, and here you can actually download the full model and try it with system modeler. Um, right. There were some questions on can we use system modeler via internet and things like that. So you once you create a simulation, you get a simulation executable. That's a .exe file, and that exe file you can host it in a server, and then you can create a REST API over it. So there are things like that. So if you want to know what you can do with the models once you have created them, uh, we have listed under connect and deploy different things one could do. So how there are ways in which you could share your models by creating cloud notebooks that you can share it with external users, or there are different ways, like you can create, once you create a model, you can create something called a FMI model, which you can then import into 250 other simulation tools. So let's say you are using simulation tool X, and you want to use your model that you have created in System Modeler. You can export it as an FMU and use it in other tools as well. And yeah, and then there are different ways in which you can uh, plug your models to real world data, like you can connect it to Arduinos, uh, industrial sensors using uh, industrial standards like OPC UA framework. And then there are yeah, there are different things that you could do, but I will not go into the details. But here in the features page, you can, if one is interested, you can find all the different cool things that you can do with System Modeler um, and Wolfram Language.
I think that's all. Thank you so much for your time. Our
Yes.
next speaker is Jeremy, and he will walk us through how Wolfram language can be used to extract, transform, and load processes, which is a very key part for modern data workflows. Over to you, Jeremy.
ETL is an acronym for extract, transform, load, which is a common workflow in data engineering. As we shall see, Mathematica is a very competent tool to perform ETL and may very well be a more productive environment than Python for data engineering. I've been a Wolfram language developer on and off for the past 30 years and in 2 different careers. Firstly, I've used Mathematica to find profitable trades in the South African interest rate markets. And more recently, I've used Mathematica to create retail market intelligence platforms based on large amounts of web scrape data. One important application of a retail intelligence platform is to compare pricing between competing retailers. The presentation today will extract product data from an online store, then transform that data to compare pricing between Checkers and Pick and Pay. Finally, the comparative pricing data will be loaded into the Wolfram Cloud. This should provide a good overview of extract, transform, and load in Mathematica. Extract means retrieve data from an import source, which could be a database, file, API, sensor, website, or any other source of data. The easiest way to get data from a website and avoid many anti-bot measures is to automate a browser. So firstly, we need to open the browser. Here we can see the Pick and Pay online store page open, and you can see Chrome is being controlled by automated test software. What we want to do is we want to get all these product details into Mathematica so we can further work with that data. So let's get that product data. And what should be apparent, I'm not going to take you through the actual mechanics of the code, but what should be apparent is it's very short, the code that you need to write to be able to get the data, which we can see here. We've got 72 products in Mathematica, product name, and price. Transform means clean, process, or otherwise transform the data into a form ready for consumption by an end user. Now, please assume we are at a point where all products sold by Checkers and Pick and Pay have been recorded in SQL databases every week for the past 3 years. Here, we're going to develop a workflow to compare the pricing of all identical products sold both by Checkers and Pick and Pay on one date. Firstly, we need to load the data into Mathematica. And this is just a user-defined function to get products from a SQL database. Here you can see Pick and Pay products, product price barcode, 22,900 products, Checkers product price barcode, 18,500 products. Then we need to clean and process the data into relative pricing between each product sold by Checkers and Pick and Pay. So now we see there's 7,500 products that are sold by both Checkers and Pick and Pay. Here are the products. Pick and Pay price, Checkers price, and the price difference. And then the barcode. Now if we have a look at this particular product, Pick and Pay price just under 100 Rand, Checkers price just under 55 Rand. Checkers is 45% cheaper than Pick and Pay for this product. Let's check that that's the case. Just opening a browser with Pick and Pay online store with that product, just under 100 Rand. And then the Checkers, same product, just under 55 Rand. So indeed, Checkers is 45% cheaper than Pick and Pay on this particular product. So this relative price difference, 45% of the product, there's 7,500 of them. We're now going to chart and we're going to put those relative price difference in 2% bins in this histogram. As you can see, Checkers is skewed cheaper than Pick and Pay with an average price difference on all of those 7,500 products of minus 3.16% as of the 16th of September. So this bar here is showing that in the -2 to -4% cheaper, Checkers cheaper than Pick and Pay, there are around about 850 products that are -2 to -4% cheaper than Pick and Pay. Here we use the production code to compute the average relative pricing of all identical products sold by both Checkers and Pick and Pay every week for the past 3 years. So previously we just looked at the pricing difference on one date, 16th of September. Here we're going to go and look at it over the last 3 years. I started this parallel computation earlier. It's going to take around 100 seconds to retrieve approximately 7 million products from 2 SQL databases. So, on average, 23,000 Pick and Pay products and 19,000 Checkers products every week for the last 3 years. So 7 million products. And then compute our relative pricing production code in parallel. So here's the parallel computation that's being shown progress here. And then this is the production code here. So we're computing our relative pricing production code in parallel on all products from each of these 166 dates. It takes about 100 seconds. So please don't let anybody tell you that Mathematica is slow. Here we see the output of that. So we have an association with the date and then the average price difference on that date. And we see that's what we looked at first. In developing the workflow, 16th of September was -3.16%. Now this is the average every week for the last 3 years. So a detailed explanation of this production code here is beyond the scope of this presentation. However, it is worth highlighting the query function and how powerful it is for working with hierarchical lists and associations of data. So Mathematica allows one to cover an immense amount of ground with a brevity of code which translates directly into developer productivity. So really this code here and then this here basically has gone and worked out checkers versus pick and pay pricing every week for the last 3 years, looking at 7 million different products. So I think that's pretty amazing. Load means store, transform data into a repository, such as a database or the cloud, ready for querying and analysis. Here we upload the time series data to the Wolfram Cloud. The time series data we calculated previously in the transform section, 160 last 3 years worth of data of the average price difference between checkers and pick and pay products. Within Mathematica, we can have a look, we can query that data that's sitting in the cloud. So the cloud expression comes back and is in here, and then I can query it within Mathematica and ask for what was the average price difference on the 16th of September, which was minus 3.16, which we've seen before. Now we create an API in the Wolfram Cloud to allow the data to be available to any client program. So here's the code for the API. Deploy it in the cloud. Let's check it out. Click on this link. And we've opened a browser with that URL to the API. It's coming back with a failure because we needed to provide a parameter. What the C date is. We could ask for all. And then we get all of the time series data back. So we get the date as the key in this association. And then we get the average relative price between checkers and pick and pay. Then we get all 3 years data here. Or we could have just asked for a specific date. And we get back for the 16th of September minus 3.16. So you can see now this API is working in a browser. You can also, within Mathematica, use the API. So here, let's get the same thing back for the 16th of September in Mathematica. Or if we want to get it all back, we just change the parameter CDate to all. And then we get them all back there in Mathematica. This is almost trivial compared to the work required to publish a Python API in Amazon Web Services. Again, it's a recurring theme with Mathematica. The brevity of code to get the job done is astounding, I think. And basically that translates into developer productivity. Finally, let's have a look at kind of a dashboard that would sit on a user's desk, and they would click a button, go look into the dashboard. Here's a very simple example. I'm going to chart all that time series data, and I'm actually going to go and pull from use the API in the Wolfram Cloud to pull the data from the Wolfram Cloud and then put it in a chart. One line of code again to do that. And there is that time series data, average, checkers versus pick and pay, relative price, observations each week for the past 3 years, the latest observation being minus 3.16%. And we can see it through time over the last 3 years there. And it's certainly clear to me that Checkers has a systematic pricing strategy relative to pick and pay. Finally, in my experience, Mathematica's help system is easier to understand and quicker to find than Python's. Mathematica's notebook environment is more robust and powerful than Jupyter. Mathematica's functional programming language produces concise code bases, which translates to less bugs, which I believe makes Mathematica developers more productive. And yes, Python is free, but developer time is orders of magnitude more expensive than a Mathematica license, which should result in a substantial savings on software projects developed with the Wolfram language and Mathematica. Happy to answer any questions you may have.
Thank you, Jeremy, for your talk. I do see there are a couple of questions in the chat. If you like to answer them now, it is a good time. Otherwise, we can always get back to them through the email for some details answer.
Yeah, let me try and answer them. Jonathan has a few questions there. I'm not sure I understand the first question, but basically what's happened here is we've written some web scraping code. We've run that code in Mathematica. We've extracted data from a website, processed it, and then put it in a database. And then we've kind of done that every week for the last 3 years. And then when it's coming to like use that data, then we're going to extract it from that database and used it. And the second question, yeah, I mean, this process that I just talked about, Jonathan, that's happening actually in an office, you know, on a server, but it could be in a data center or in the cloud. So yeah, I mean, really, wherever you can, you know, run code, it could happen. Your next question, Jonathan, about creating an API inside Wolfram instead of the public cloud. I might stand to be corrected here, but I mean, within Mathematica, you actually write and test the code of the API, and then you would publish that in the Wolfram cloud. So it would be, I think maybe Farid could answer this better than me, but you can start doing this in a private cloud, but then you need an enterprise edition of Mathematica. So yes, I mean, you can basically do whatever you want to, but there might be different costs involved though.
Yeah, Jeremy, I think you pointed that correctly. So it basically depends on how you want to deploy it. And there are different ways to do that. And all these things are possible. Thanks, Jeremy, again, for that really deep dive into the data engineering. So let's shift gears to education and learning now with Arban, who is also the Wolfram certified instructor at Wolfram Research. And he will present about and he will showcase how educators and students can leverage Wolfram tools to enhance learning experiences and streamline workflows. It's also a good tool if you have been using Wolfram language for 30 years and you want to optimize how the programming works in the Wolfram language. This is a very good tool to start using that. So let's welcome Urban. Over to you. Thank you.
Today, I am quite excited to tell you about how to turn rough ideas into computation with Wolfram Notebook Assistant. Now, typically in our webinars, or at least in the ones I run, we'll have a bunch of pre-populated stuff in our notebook here, and I'll kind of, teach you about a topic. Here, I think it's better to just kind of see it in action and kind of learn through that seeing. I think at this point, we're all familiar with ChatGPT. And I would say that Notebook Assistant is like a custom version of ChatGPT that has access to all of our documentation and all of the data that makes, say, Wolfram Alpha so powerful. It knows, all of the functions in Wolfram language. And if you go to the documentation, you can see that there are over 6,300 as of the most recent release functions. That's quite a large number. It's nice to have a computational assistant for that. Knows about all the tutorials, all the examples, and like I said, it has access to all the data that powers Wolfram Alpha. It can improve your code, it can explain code that you got from somebody else, and as is the primary focus of this talk here, it can turn your rough ideas into computation. So Notebook Assistant, in summary, works like a hyper smart, fully knowledgeable helper that lives right next to or inside of. You can open chat cells in a notebook just by typing an apostrophe. It just lives next to your notebook or inside your notebook. And if you want to use Notebook Assistant, you can sign up for Notebook Assistant and LLM Kit, and there's no configuration necessary. As soon as you kind of sign in to activate your product, it's all linked to your account and everything will just work. So let me show you some examples. We'll start kind of simple. Say I'm brand new to Wolfram Language and I want to know how to do kind of a basic programming task. Let me say something like, let's say, how could I find the running maximum of a list? Actually bump the magnification here. It's a little bit small at 150 on this monitor. Maybe that's better for folks. And then I can just press enter. This gets sent to the assistant. And this gives us a nice little answer here. So in Wolfram Language, we can use the fold list function. And here's an example of how this would work if we had some sort of list. And here, note that the function here is linked. So if I click this, this has actually opened up the documentation page so I can read all about this particular function that the assistant has linked. So here it gives us an example of this running. And then it also notes, and I think this is kind of a neat thing, that this has access to this through our documentation, that you can use this resource function that kind of automatically does the task that we've asked it to do. Resource functions kind of extend the functionality of Wolfram Language. The way I always put it is, if you think 6,300 built-in symbols and functions isn't enough, if there's like some specific thing you find yourself doing really frequently, and you think maybe somebody else might like to use that, we have this thing called the function repository, where users and people from Wolfram here, we can all submit functions to the function repository, and then everybody can access them after they've been approved by us. And this will just grab the function right from the cloud, and we can just use it right in the notebook. Now, Notebook Assistant gives us this answer, and it gives us this code. And something that's quite useful is you'll notice that not only can we copy the code, we can insert and evaluate the code here. So if we click this, we get this, and we can see that indeed for this example list that it has come up with, at first, the largest element is 3, starts at 3, and then it stays at 3, and then 5, 7, and then once it hits 8, we stay at 8 because 8 is the largest entry. 7 isn't larger, 5 isn't larger. Once we hit 9, we stay at 9 because 9 is the largest entry, and there we go. So that kind of does what we'd like. Maybe we have an image in our notebook. So let's say we've got some cats. We'll just call it that. If you're new to Wolfram Notebooks, for reference, you can just copy and paste images right in here. You can also use the import function or drag and drop things from your file explorer. All of that stuff just works transparently. And once it's in the notebook, it's a fully computable object that you can do whatever you want with. It's really, really, really useful and nice for folks who do image analysis in particular, but it's also nice for, a hobbyist. And again, I've been in both of those positions. I've done some image analysis for things in a lab in grad school and just on my own. And I have a little example coming up to show you that. But now that I've got this cats here, I could say something like, how could I find where the cats are in the image cats? So here, it asks us to do this. And it tells us this is this function that could be used for this. This is actually, this is not something I was aware of. This is a new one. And so we go in here, it's giving us coordinates for where the cats are located in the image. There are a couple of different ways you could go about that. And, I'm going to ask and see if it's willing to suggest to us a different way, maybe. So 2 things to kind of notice here that I'm doing, again, a bit transparently. I ask, is there any other function that could do that? And it knows that I'm referring to this previous chat here and what we have in the notebook. So the Notebook Assistant is aware of the whole chat history above it, and it's aware of everything that's in the notebook over here that it's focusing on. And how can you choose which notebook to focus on? Right here, if you just click this, you can choose any notebook you have open. And you can also just have it choose automatically, which is the default. And what that will do is it will just focus on whichever the last notebook is that you've clicked on. So let me click this, any other function that could do that. Yeah, so you could use image contents perhaps. And then here we get a nice little data set where it says, okay, we've looked in the image of that I've called cats here. There's nothing special about calling it cats. It's just what I've called it. And we're able to see, oh, okay, there's a domestic cat, and this is the little thumbnail, and another domestic cat, and this is the little thumbnail. And here are the rectangles that are the bounding boxes for these cats. And here are the confidences that this thing has, that this thing is a domestic cat in each case. So that's pretty nice, if you ask me. You can also ask kind of questions that are a little more, let's say, Wolfram-y in a way. Questions that take advantage of kind of the curated tower of knowledge on which Wolfram language rests. And you'll see what I mean by that when I ask, how could I make a 3D plot of the terrain around a mountain? Okay, so it's letting us know about these functions. Here's the thing. As an LLM-based thing, sometimes Notebook Assistant will hallucinate. I found it's actually quite good about not doing that. It really knows when to use Wolfram Language and the Wolfram Entity Framework to get real hand-curated information rather than just crawling the web or using training data or using information that was in the training data. But even in the cases where it might hallucinate, you still get links to useful functions that you can check out. And so even if you can't quite get it to work, this is always a good starting place. But let's see if this did work. So let's just insert and evaluate this here. And that works, no question. So here we can see that we have used the geo-elevation data function here to get Mount Everest as kind of our center point. And then we're kind of looking at a 4-kilometer block around this. That's going to be our data. And then here, it has put that data into a list plot 3D. This is a function you can use to plot a list, which is a Wolfram language generalization of an array. And here, it just plugs it in, and it even cleverly, I do think this is actually quite clever, is it uses the mesh functions option and then specifies, this is kind of a pure function notation. It's like a lambda function if you're familiar with that. If you're not familiar about it, don't worry about it. It's not a big deal. You can always check the documentation if you're curious. But what this mesh function does is it's getting the third coordinate. That is, we think about the X, Y, and Z coordinates in a sense. It's getting the third coordinate and it's drawing nice mesh lines on there. And it's doing that because contextually it's aware that if you kind of want to look at elevation data, you often want to have these lines that indicate how high up you are, these lines of constant elevation. And that can give you a sense of how rapidly the topography is changing. So here we see it's very steep. We see a bunch of lines gathered together, whereas here the topography isn't changing too much. The elevation is pretty constant, so we don't see too many contours there in a sense. And now, because the Notebook Assistant is aware of the previous conversation and of what's in the notebook, I can say things like, oh, that's great. People go back and forth on this, but I have tended to notice that when you're dealing with an LLM, being polite does get you generally slightly better results. This might sound a little bit kooky, but if you think about the way LLMs are trained, right, they're trained on a bunch of training data. And generally in the training data, when you have somebody kind of politely asking a question or having a conversation, the responses to somebody being polite are going to tend to be a little bit better. So let's say, oh, that's great. Could you make it so the color of the plot depends on the height? Okay, so it gives us some new code here. And if we just insert and evaluate this, we get indeed exactly what we wanted. We can see that we've got a rainbow color scheme here that was just kind of the default that was picked for this. You can ask for other color schemes if you know about them, or if you kind of want to just get roughly close to like an idea of a color scheme you have. But there we go. We're able to pull in this geographic information through the geo-elevation data function. And we're able to pull in all this surrounding information about, what is Mount Everest? Where does it exist exactly? What are its geo coordinates? All that stuff just happens transparently in Wolfram Language. And then it's even easier here because you don't even have to have known about this stuff. You can then just ask Notebook Assistant, and not only does it do it for you, but because it provides the code, you can look and you can start to get a sense of like, oh, this is pretty neat. I bet if I put in, another mountain here, let's say, is that right? Is that how we think about that? Then I could run this again. And here it is for K2, different mountain. It's actually quite interesting the way that looks there. Maybe if we have any volcanologists in the audience, they know exactly why it looks like that. But to me, a layperson with respect to mountains, which is not a sentence I find myself saying frequently, I think that's quite interesting topographically. So that's just kind of a little example of being able to write code that pulls in functions that use real curated data that we have access to through Wolfram Language. You can maybe take a step back and do something maybe a little simpler in a sense. Maybe you were working with some graphs. Not graphs in the sense of like the plots of a function, but graphs in the sense of like a network. So maybe I have a graph and I want to swap the nodes and edges. I can just ask about it. Okay, so it suggests using the line graph function, and then it comes up with some example code. So suppose we have this original graph, we can then swap the nodes and edges by using this. And if we click on here, let's go ahead and not suppress. A semicolon suppresses output. So we're going to leave the original output of the original graph. We're going to see that this is the original graph, and this is the graph with the nodes and edges swapped. So now not only do we get a result, but again, we can see an explanation for what the code is doing, and we get to learn about the function line graph. And again, if we click that, it pulls the documentation right up. And again, for folks who are newer to Wolfram Language in particular, there is something I want to note about the documentation. Well, a couple things really. One, the documentation is really good. We spent a lot of time making sure it's very thorough, has a lot of useful examples and details, even things like neat examples. But maybe more relevant to the Notebook Assistant is maybe it gives you a function and it's really close to what you're asking for, and you can't quite figure out how to ask for exactly what you want. What you should do is you should just click on that function name, come to the documentation here, and look at See Also. And in many cases, if the function that was suggested isn't quite the one you want, you'll be able to find the one you want and See Also here. So you could click in here and say, oh, okay. Well, this is what I wanted. I actually wanted to get the graph complement here, which does this. And then you can look at all the examples, and maybe this one isn't quite what you want. Maybe you say, oh, I wanted the graph intersection or something like that. And it's all just there in the documentation. And if you have any questions about anything in the documentation, guess what? You can ask Notebook Assistant about it. We can do things like, suppose that I've got a CSV file and I need to make a plot. Well, that's a very common use case in my experience. So it might be something where, again, if you're new, you might not know how to do it. So you could say, how could I make a plot from a CSV file? Okay, so it gives us kind of all the steps. We should use the import function to read the data from the file, and then use a plotting function like list plot or date list plot. Importantly, not just the plot function, which plots functions rather than data, but list plot and date list plot, which are what we want for a CSV. We can use those, and there we go. And here it gives us, how do we import something? And then it says, here's how you would plot it.
Thank you, Urban, for the insightful presentation. And I asked a question that if we can do a real-time image analysis. And while I was listening to the talk, I just used Wolfram Notebook Assistant and I asked it the same question, and it just gave me the whole way how to do that by using the current image of using my laptop and then applying the image contents in the real time. So yes, that is possible. And that is where, even if we are using Wolfram Language for 15 years, the Wolfram Notebook Assistant helps us a lot and makes the process much, much quicker for us. So thank you again, Urban, for your talk. Let's move forward with our last talk of the session, which is being given by Ryan, who is a research assistant at FinPix, and he will demonstrate how Wolfram tools can be used to build robust financial models and extract actionable insights from that data. Over to you, Ryan.
Hello, my name is Ryan Lovejoy. I'm currently working as a research assistant at FinPix. FinPix is a fintech startup company attempting something quite ambitious. We want to redefine how financial information is understood, shared, and acted upon. Today, I'd like to show you our consultation tool. This is a live decision-making tool that can be used in the boardroom by shareholders, investors, and upper-level management to help inform them of the potential outcomes of their decisions. Now, if you've ever seen a financial report, you'll quickly agree with me that they are often dense and confusing. They're built on sprawling spreadsheets that take weeks to prepare, with hundreds of calculations that are riddled with errors, and actually only one person on the team understands. This often leads to a lot of uncertainty. FinPix asked the question, can we do better? Our problem set became, can we find an algorithmic approach to financial modeling that avoids manual spreadsheet work? Could we use algebraic logic to build models that are mathematically rigorous and error-free? Could we visualize these outcomes interactively and clearly so that it could be understood by all stakeholders? And lastly, could we generate timely reports that reflect the latest business realities and not last quarter's post-mortem? Now, when we began FinPix, none of us were expert programmers. Our team consists of financial professionals, turnaround consultants, and a few engineers. What we needed was a platform that would be forgiving but still expressive. Something that would allow us to build computationally and visually in the same breath. Wolfram Mathematica provided exactly that. With its simple-to-use, pattern-based language, we could go from idea to prototype within the same notebook. As a research team with constant development, this was instrumental to our rapid prototyping and emergent design to get software in front of potential investors. And perhaps most importantly is Mathematica's dynamic module system, which allowed us to build real-time, client-facing dashboards that are both responsive and beautiful. Let me show you what I mean. To begin this demonstration, we have an input interface designed to capture the historic financial information of the company, beginning with the balance sheet. Here, users can update how many entries they want considered, select the relevant dates, change the document currency, as well as input the company name. The income statement page mirrors this flexibility whereby again, the user can update how many time periods they want considered, whether they're monthly or annual figures, as well as use a built-in import-export system to quickly populate or save any of the data entered. Using built-in operators such as buttons, input fields, and pop-up menus, we're able to achieve state-aware reactive forms within the same notebook. Mathematica's visualization tools then enabled us to turn this raw data into geometric shapes with just a few lines of code, visualizing the ratios and proportions present in financial information. Seen here is the FinPix SOFP, a visualization of the balance sheet using the Pythagorean formula. Here, an intuitive angle forms between assets and liabilities that we call the state of solvency. In this test company scenario, they begin with their assets being larger than their liabilities, which gives them a positive angle. As they begin to trade, they are selling out assets, perhaps taking too many loans, and before they know it, their liabilities is now greater than their assets, giving them a negative angle. This image also helps capture the proportions between current and non-current assets or liabilities, which further indicates the health of a business. The income statement page shows the historic ratios between fixed and variable costs, while giving an indication of profit or loss. This test company is clearly underperforming. The image helps show the stability of fixed costs, as well as the proportion between fixed and variable costs, which helps identify which costs to target during turnaround discussions. Next, we're onto our assumption sheets. This is our sales matrix, a tool used to assess the risk of future sales ambitions, as well as discuss gross profit improvements. Seen here are also time variables for each change. This is the time it would take to implement. Next, we have our fixed cost cutting image. This is a rows diagram that captures the proportions of a few aggregated fixed cost expenses. This gives us an environment to show the ratio of improvement in each field. I've also simply coded in a few initiatives that, once saved, a company can quickly switch between different strategies. Next, we're on to our SOFP restructuring page. Here, we discuss the capital injection required by shareholders to improve the solvency of the company. By increasing the assets or decreasing the liabilities, we're able to improve that angle to a more positive one. Now, this is not always required, and this image would then just be used to show the redistribution of capital within the company. I'm sure by now you can see that Mathematica has become more than just our coding environment. It has become our design studio, our simulator, calculator, and even presentation layer. At the heart of FinPix is the VFC model. This model originated in the PhD thesis of our founder, Dr. KJ Gribnitz, a thought leader in turnaround research. The model replaces the endlessly complex spreadsheets used in traditional turnaround planning with a compact algebraic engine, seen here displaying the accumulated cash flow of a business. By combining a handful of inputs from the assumption sheets before, the model produces a multi-scenario risk assessment within seconds. Here, the different colors represent delays in hitting their targets, And with a few algebraic expressions, we can quickly determine when the company will break even, how long it will take to turn around, and most importantly, what it will cost. And the magic? With a simple touch of a slider, we can showcase the implication of not hitting their implementation targets. And if the turnaround is too high or the funding is going to be too much, we can quickly manipulate the plan changes to reach their goals. Creating an iterative decision model whereby the user can now go back to the assumption sheets and cut costs further or improve sales. From here, we project growth rates on what we call the stable state. A simple low and high growth rate is used as further multi-scenario assessment on the potential growth of the company following a successful turnaround. With the help of Mathematica's built-in 3D graphing functions, we can then combine the 5 delays with 5 growth rates to achieve a 3-dimensional present value bar graph. Here, the cost of the turnaround, shown as yellow bars, is compared to future potential profits, shown as grey bars, to achieve a 3-dimensional net present value bar graph. We then use this data to form our IRR frontier, an internal rate of return, a clear indication of which strategies will return a profit after 5 years and at which delay serious intervention will be required. This evaluation report acts both as a simulation tool and a communication document, one that captures the financial logic, the assumptions, the risks, and the potential outcomes of a proposed strategy. It is verifiable, repeatable, and clear. This platform has allowed us to work like applied researchers, not just coders. We can build reusable templates for different industries, whether they're startups, distressed companies, or profit companies seeking to understand the returns of an investment. For a small team with limited dev resources, Mathematica gave us what no other language could: the power to go from concept to client in a single environment. Now, this is a version from March, a prototype containing half of the inputs and sliders we aim to achieve to have granular detail. Since then, we have made major leaps in our fundamental principles, combining the interrelationships between balance sheet and income statement. A separate tool called the verification report, a statistical tool underpinned by Bayesian inference theory, is also seeing accelerated development as we aim to verify the strategies undertaken by management. And the good news, Mathematica is scaling with us. The new LLM assistant is exactly what we needed to further explore the capabilities of Mathematica, optimize our code, and venture into the unknown. To close, I want to highlight what FinPix stands for. We believe financial understanding should not be at the privilege of CFOs and spreadsheet jockeys. It should belong to every executive, every team, and every company looking to make bold decisions with confidence. Mathematica has given us the tools to make that happen. It has allowed us to visualize cash flow, stress test decisions, and turn math into meaning in real time. As we continue building, testing, and presenting this tool in front of our clients, we're reminded every day that clarity is power. And thanks to Mathematica, we're proud to be putting that power into the hands of decision makers when they need it most. Thank you.
Thank you, Ryan. And thank you to all our speakers for sharing your expertise and passion with us today. As we do not have any further questions, so we can bring this to the end of our first ever South Africa Wolfram User Conference. And it's really a fantastic journey it's been. I again give a huge thank you to all our speakers for sharing their expertise, and especially to all of you in the audience for being part of this milestone event. So, either you are an engineer, educator, data scientist, senior scientist, or just curious about computational thinking, we hope today sparked new ideas and possibilities in your mind.